Exoskeletons have the potential to augment human mobility and have already demonstrated metabolic cost reductions in walking. Recently, in the Collins lab, we have developed an exoskeleton that applies torques at the hips, knees, and ankles. With this many degrees of freedom, it could be difficult to find candidate assistance strategies. So, for this project, we wanted to use simulation to find hip, knee, ankle exoskeleton strategies that could assist walking. We hope that these could be used as starting points for human-in-the-loop optimization experiments. For our project, we have two main research questions. First, how can bidirectional hip, knee, ankle assistive torques be optimized to reduce the metabolic cost of walking? Second, how do the optimal assistance strategies at each joint during single joint assistance compared to the profiles when all three joints are optimized simultaneously? For our project, we use the OpenSim API in MATLAB and a 10 degree of freedom AT muscle model from Ong et al. 2017. We estimated joint torques calculated from inverse dynamics data from Edith Arnold. We used a fixed kinematic approach, so the kinematics were not changing in our optimization. First, we used a muscle redundancy solver to find muscle activations without any assistance. We then added ideal torque actuators at the hips, knees, and ankles, and then solved for both muscle activations and exoskeleton assistance torques, while optimizing to reduce activations squared. Afterwards, we estimated metabolic cost for the optimized activations.
Our first step in the project was comparing how our simulated assistive torques with the exoskeleton capable of delivering 200 Nm of torque compared to joint torques from inverse dynamics. We see that the assistive torques closely match the biological torques. However, pilot experimentation in the Collins lab has shown that walking in this device with such high magnitude torques is nearly impossible. These results do indicate that using exoskeleton torques with a similar profile but lower magnitude than biological torques could be a good starting point for exoskeleton torques. After optimizing for activation squared with different levels of assistance, we calculated the average metabolic rate. The exoskeleton is capable of driving the average metabolic rate down as the magnitude of applied torque increases. As we saw in the previous slide, the exoskeleton assistance essentially attempts to replace the biological joint torques. When the maximum allowable torque is unable to match the biological torque, the actuator saturates, as in the 60 Nm torque at the ankle. We also looked at the muscle activations during exoskeleton assistance. These are just a few representative plots, but we see that as the assistance increases, the muscle activations fall. During 200 Nm assistance, the muscle activations actually drop all the way to zero, which is not something we see in experiments when we measure surface EMG. Next, we wanted to look at how the simulation changed when we actuated a single joint as opposed to actuating all three joints simultaneously. When we do human-in-the-loop experiments, we need a small parameter space to achieve convergence. This is easier if you optimize a single joint, but we wanted to know whether you would get the same results optimizing one joint at a time as opposed to all three. We see that the exoskeleton torques are similar between the two conditions, but the single joint profiles are slightly higher in magnitude in general. The muscle activations also show interesting behavior for single versus multi-joint assistance. With single joint assistance, uniarticular muscles such as the soleus experience complete deactivation when their joint is active, but no reduction in activation when the other joints are activated. Biarticular muscles change activation differently depending on the actuated joint, indicating the importance of considering the coupling in multi-joint exoskeleton assistance.
In the future, we would like to optimize for estimated metabolic cost. We are unable to get those optimizations to converge, but candidate solutions like the one shown on the right are promising and seem similar in ways to the results from optimizing for activation squared. We would also like to test candidate parameterizations in simulation to see if we can reduce the parameter space to something implementable in human-in-the-loop optimization experiments while still capturing the main features of the assistance strategy. In conclusion, lower magnitude assistance than biological torques, but with similar timing and features, could be a good starting point for testing assistance in experiments. And finally, it seems that multi-joint assistance could require lower magnitude torques in comparison to single joint assistance. We would like to thank Nick Bianco, Chris Dembia, Tom Uchida, Carmichael Ong, and Rachel Troutman for guidance, technical help, and sharing of software resources. We'd also like to thank Scott Delp and Melissa Boswell for guidance and for organization of the AME 4D5 class.